Okay, I don't see anything. Let's wait a few minutes and then we can officially start it.
Hey, I think we're almost ready.
Okay, let's start.
I see people joining. Let's start. Welcome everyone to our monthly Leios update, our first in 2025. Happy New Year to everyone. That's the first time here and that I haven't seen. It's also our first live stream. Today is January 29th. And similar to past presentations, we have updates from each workstream. We start a bit out of order today with the Haskell simulation coming first. And we then continue with the cryptography chapter presented by Brian, who will give you a high-level update around the Leios voting and what certificate options the team is considering. Followed by research, where Jürgis is going to present a new approach which the team is favoring, that reduces the certificate size and how that is stored in the past blocks. And after that, we have Yves and Andre presenting their update from former methods. And last but not least, our last two work streams that relate to our simulation work, including the Haskell one from the first item. The first one here is the DataQ approach, DataQ system design. And lastly, we have Sunday Labs demoing their progress for the REST simulation. Before handing it off to Duncan, I want to give a high-level overview of why we have these work streams, especially for new listeners. This slide is a bit small maybe, but I'll go over it briefly. You can see that each work stream is being represented as a box here, indicating like their influence to each other. This is obviously just a very abstract notion, but should bring across like the interdependencies and checks and balances that we have in place. And to highlight a few, research is a large driving force that guides and iterates on design based on new knowledge gathered from the simulations, for instance, or benchmarks that come from cryptography and similar. But more importantly, each workstream serves a very specific function, which is to find like the optimal protocol implementation at some point. So we want to maximize transaction throughput while balancing network capacity and computational resources used by the underlying nodes running the system. And that's what's basically here indicated as a blue box. We also strive to be transparent with our findings and rely on your feedback, specifically the SBO community as well as the builders community. So questions are very welcomed and we address them after we've gone through the slides. And with that, I want to hand it over to Duncan.
Thanks very much. Yeah, thank you, Will. Yeah, Will has kindly allowed me to go first because I need to leave by 1:30. But that also means if you have any questions for me, ask them in my segment because I won't be around at the end. So I'm not going to do a show off a new visualization because there's nothing very new and exciting on that front. But I'll focus on the bits we've done and particularly what we are planning to do in the next PI. So not just the next month, but the next PI, which is 3 months roughly. So recent updates: we met our previous PI goals, and we've now proposed some new ones. We're soliciting feedback on that. We've been synchronizing with the Rust and DataQ simulations models on common file formats, sets of parameters, so that the different implementations can share those inputs, so that we can get closer to comparing like with like, particularly the sets of parameters. We can also generate now random topologies in the common format. Historically, our simulation always worked with randomly generated topologies, but we now have support for reading in specific topologies and exporting the ones that we generate. Minor feature: the simulation now supports bounded or unbounded CPU parallelism. Previously, it was just sort of hard coded as each node had one core effectively, but now we can have some n number of cores that's configurable, or it can be useful for comparison purposes to pretend that you have unlimited CPU parallelism. We have, and I'll come back to that because that's a sort of a theme that we'll talk about later, is degrees of realism. We did comparisons against the real Cardano benchmarks produced by Cardano's benchmarking team. They put out reports on this which are excellent and give us something to compare against. And when we try to get the same kind of parameters as the benchmarking team use, then we are getting in our simulations block diffusion within about 10% of what the real system is doing. It's slightly hard to account for all the details. Obviously, there's huge numbers of details particularly in the real system. But actually note that the real system is 10% faster than our simulation. And we think probably the reason for that is that the real system implements block header pipelining, and we do not, and that saves latency. And we are hopeful that we will in fact not need to. 10% is indeed pretty close. We were very pleased with that, of course. So we're hopeful that we will not need to implement header pipelining for Leios, which would save on a bit of complexity. But that's one of the things we'll be able to, hopefully we'll be able to demonstrate whether or not it's important. So for the next PI, our goals are hopefully aligned with the sort of overall project goals. We want to be able to do larger runs of the simulation to illustrate how changing this parameter affects the outputs, like resource use, overall throughput, latency, etc. We want to be able to, the whole project, we want to be able to see what does it look like if you run at this level of throughput and then you multiply it by 10 and by 10 again. What do these different orders of magnitude look like within the system? We want to obviously make progress on the testing against the formal spec, which partly relies on completions within the formal spec, but also we've been discussing how exactly to strategy for matching those up. We want to, it's hard to make a formal commitment on the integrating modifications from research, but as far as possible we would like to keep up with protocol variations that come from the research workstream. In particular, you may recall when we did our demo last time, I was saying you can see from this visualization that we have these big bursts of votes that go around the system and make everything slow down for a while, and that we had suggested that it would be nice if we can to spread out the way that the votes are generated over time, so it's more even. And research workstream has done exactly that, and so we now need to see how that works in our simulation. So try the update, the change to the way the votes are done within the short Leios pipeline, and hopefully we should be able to demonstrate that it has the intended effect. So that's the kind of thing we want to do, plus any other new variations that come up that are important. An interesting one is that we would like to structure our simulation so that you can turn on or off different aspects of realism within the simulation, and use that to do an analysis, a little bit like the parameter analysis I was talking about before. Like, you adjust the parameters and you see what the effect is on the input and the output. But in this case, it's changing the degree of realism within the simulation, so that for a couple different purposes. One is for stakeholders to try and help gain confidence in the results that we're seeing. Because if you just see like, well, here's a simulation, it produces these results. Well, how do I know that those are in any way reasonable? Because it's very hard to, give correctness criteria for performance results. So the idea is that we start with a baseline which is obviously correct because it's based on a very, very simple like graph algorithm, all pairs, shortest path, some ideal model of not Leios overall, but of diffusion of blocks, of the different kinds of blocks within Leios, and then compare that with our with our simulation, where we turn down the realism and get rid of all kinds of sources of latency, and then step by step add them in one at a time, so that we can quantify what aspects of realism introduce how much latency, and hopefully that should demonstrate give other people some degree of confidence in the results that we're seeing. But also I think it will help us to to identify what are the major sources of latency. How does real world latency deviate from a simple, much simplified ideal. And it'll also help us, we hope, to compare against the simulations from another work stream. In particular, the DataQ, we should be able to get very close to, by turning down the realism, we should be able to get very, very close to what the DataQ results show. That is our hope, and we've had some useful discussions towards that end. And then finally, we would like to do a draft report primarily to the Cardano network team, but other readers as well, based on our prototype that we've been implementing, our proposals for the new network mini protocols. So that gives a step towards it'd be a stepping stone towards a real implementation by documenting that and soliciting feedback. So yeah, that's what we are intending to do in the next quarter. Any questions? I see Charles has just turned up. Oh, yeah.
Good to see you, Duncan.
Any queries on anything? Otherwise, Will can hand on to the next person.
Next up is Brian.
Thanks.
Okay.
Thank you,
Will.
Thank you, Duncan.
Yeah, so I'll give you an update on what's going on with voting and certificates. We've made a good deal of progress on converging on viable designs. One of the things we're trying to do in this PI is to have very concrete evidence to show the viability of one or more voting and certificate designs. The voting and certificates works interacts perhaps with other work that's going on Mithril, Leios, Midnight. So there may be a common solution for that, but we want to make sure we catalog viable solutions for Leios. And there are a few tensions here. Obviously, for security reasons, we need safety and fairness, that adversaries cannot control the endorsement process. And liveness means that adversaries cannot interfere with the endorsement process to prevent it from happening or slowing it down. So, and we want to do this in the presence of very strong adversaries. We want the protocol to keep running. Now, given that, we have some desired requirements and properties. We want things to be fast to verify the certificates. We want to be able to create them fast. We want them to be small. And we want the key management to be very straightforward and a low burden on the system. So these tensions really interact a lot, and that's the space we're working in. And I'll show you the next slide, which is Some of the things we're looking at a technique called ALBA, and this is a way of compressing information in a certificate. BLS is essentially the way Mithril has been historically doing certificates, and Musen is an up-and-coming variant, uses BLS, but it has some aggregation and key evolving properties. So we've been carefully looking at all these and doing that in close coordination with the cryptography and research team. So Raphael is on the call. I think Dimitar is on the call to answer detailed questions about some of these. And there's no clear win here. Each of the methods has some pluses and minuses. ALBA is really nice in many respects, but we're struggling a bit with some of the details of liveness on that. The Mithril style is quite viable at this point, so we know that there is a path forward to have certificates on Leios. And then Musen, even though it has some nice properties, it's a little bit weak in some areas compared to the BLS Mithril style. So we'll go to the next slide. One of the things that the cryptography team is very deeply looking into is zero-knowledge proofs and how that can radically shrink the size of Leios certificates. And that research is across multiple projects, not just Leios. And this would give us very small certificates. The big concern is that it might take a long time for nodes to create these certificates. So we have to put numbers on that. We also know that verification will be really fast. So if the proving time is sufficient, we might be in a really good spot there. So we'll keep giving you updates on that. That's ongoing research. In the absence of that, we want to have non-ZK methods of doing Leios just to prove that Leios truly is possible. Next, we've been doing detailed benchmarking. So these benchmarking measurements.
Dimitar.
Oh, yes, Dimitar?
Just, Brian, sorry to interrupt, but could you maybe go back to the previous slide? So this proving time, I don't know if we updated you on that, but basically over the last 2 weeks, we did some experiments with basically concurrently generating proofs, and they showed very promising. So we could use GPUs, for example. Is that something that could be considered here?
Definitely, yeah.
If the
We might
time
end up
is
with
the bottleneck. Yeah.
We might end up with both a non-ZK solution and a ZK solution, and they are going to have trade-offs, and there would be discussion with Intersect and the community, like So we want to show viability of these methods, and definitely we want to show the viability of the ZK.
So Stefan's stream on TE has some work that is done in this direction, just that.
Right, yeah.
The web.
I think the big message here is this is a very active area of research. There's a lot of brain power going into it, and it's becoming more and more practical. But as of this moment, it's not practical. The BLS probably is practical as of this very moment. Next. So we have been doing detailed benchmarking, and what this is for the overall evaluation, but these numbers are actually going into the Haskell simulation and the Rust simulation and the DataQ simulation, so that as they're simulating CPU usage, as you heard Duncan say, these are the numbers that are going into that. So we can make sure that the CPU budget is realistic for what the actual cryptography would be. And so I'm not going to go into the individual numbers, but overall, they're very promising. There are no red flags here or anything. Next. And here's just more study. We've been looking at a lot of detail of how big the committee size would be, which means how many signatures you'd have, how that affects verification time. So the message here is we're really going in deeply into this to make sure that things are practical. And the last slide summarizes where we are. Unfortunately, at this moment, the liveness properties of ALBA are not quite sufficient for us. This may be debatable, but it's definitely not top ranked. But if you have the ZK proofs, that could change. The BLS is quite viable. And even though Musin has some very nice properties, it's really not adding enough to the BLS mithril style to make it worthwhile pursuing that. Once again, we might revisit that. But that's sort of the snapshot on the voting and certificates. We're working closely with the cryptography and the research teams, and I think Yorgos is going to go into some new ideas on this next.
Okay, so Brian talked about benchmarking, the current candidates, but we were also actively trying to improve our voting and certification process. And as Brian said, the most promising candidate currently is BLS without snarks. However, there's still an inefficiency, if you think about this, deploying this in the real world, which is that the certificate size is the same order as the block size of browse. And in Leios, one certificate is included in each browse block. So if the certificate size is that large, then this means that you cannot use the browse blocks for other things such as regular transactions, non-Leios transactions. And the main problem, and this problem comes mainly from the fact that voters are elected through sortition, some kind of random lottery, and then these voting eligibility proofs need to be included in the certificate. And without snarks, we don't know how to compress this information. And this is the main factor leading the certificate size being big in this scheme. So we're going to go next one. So, and I forgot to say, the BLS scheme is IOG research, is produced by IOG research. And our observation here was that, if you don't need eligibility proofs, you don't need to include eligibility proofs if the voter selection is deterministic. If you don't do these lotteries, then you don't have eligibility proofs, and then you would probably be able to save size or reduce the size of the certificate. And it turns out, I think that's quite nice, that IOG research already has thought about this, and there's this fait accompli paper which does deterministic selection of voters or whatever committee members to reduce committee size. So the goal there was a bit different. But we can use this research from IOG, this other research from IOG, combined with the BLS scheme and this observation about eligibility proofs, and get really, really nice results. So our first back of the envelope calculations seem to indicate that a large fraction of the voters will be selected deterministically for the current Cardano distribution, which means that we'll have an order of magnitude decrease in the certificate size, and that the network footprint can be cut in half. So this, I think this is a really, really exciting news, making the our path to production really seem quite easier, if you want. The only last thing I want to say here is that this improvement, this optimization, is an optimistic one. It depends on how the Cardano stake distribution looks. But it should work nicely as long as as SPOs have a stake that's close or larger than the stake indicated by the decentralization parameter, basically. It doesn't have to be exactly with this stake. It can be a bit lower, but it cannot be that everyone has a really, really small stake and then we expect this optimization to work. So that's my update. I'm quite excited about it.
Thank you, guys. Next up, we have formal methods. I believe Andre is presenting.
Yes. Yeah, so we have a nice update from our side. So first, like a small reminder, we in the past we've shown this diagram, which is a little bit smaller on the slide here, but is sort of the state machine of the Leios protocol, of a single node in the Leios protocol. So what we did in the past is formalize this state machine, and so since the last presentation, we've now added a correct implementation of that. So that means that we have, well, we can run the state machine, and it comes with an automatic correctness proof. So any step that is computed by this step function that we have must correspond to a step in this diagram, basically. So the plan for this is then, so this is one path for conformance testing of Leios. There are technically multiple paths, and we're thinking of kind of trying all of them. But this is, this is the one that we currently have. And so I think the most kind of interesting thing here is to just show sort of what this looks like. So I can share my screen, hopefully.
Yep, you should be good. Also stop presenting. There you go.
Okay. So I hope this is visible to everybody.
Yes, you're good.
Okay, yeah, so this is kind of the small test file here. So I think the first thing to highlight here is these first two things. I mean, you don't have to fully understand what's going on with all this code, but here we have this step relation, and this is effectively the relation that we just saw in this picture. So I can go to this definition, and here we see sort of all sorts of preconditions that need to happen. And this is actually a deterministic variant of the state machine. So here we're kind of forcing certain actions to be in a certain order. This can be seen here. So we, for example, we first try to produce an IB, then an EB, then we try this vote 1, and then we try vote 2. And in the non-deterministic version of Leios, you can kind of do all of these in parallel and do them in any order that you want. And just to, so I can go a little bit down here. So here we have some not so complicated theorems, but they might look complicated. But really, the key thing here is this proof down here, which says that this is the deterministic step relation from this file. And here is the non-deterministic step relation with a slight variation that allows us to do sort of multiple steps at once. And so this is a proof that says if you can make a step in the deterministic relation, then you can also make the same transitions in the non-deterministic version. So this kind of, just to show how this then all relates back to this original relation. And so here, so we have this compute proof type, and this is basically just to show you, okay, we have produced something. So compute proof, which I'll be using down below, has this type, and what this type basically means is that so this computation result it can either be an error message, which is then a string in this case, or the right-hand side is it produces an output and a new state together with a correctness proof. So that from the initial state with the given input, you can produce the output and go into this final state. So this, by the type, this has to be correct. And then down here, I'm just basically showing you, okay, compute is just sort of throwing away the correctness proof in this case. And then this is the function that we're actually using, right? We already know compute proof is correct, so we don't need to keep this proof around. And then, so down here, I have a bunch of test cases. So we have some kind of initial state that we're getting from somewhere. And here I'm just submitting a transaction. So this could be a list of transactions, but I'm just saying, okay, I submit some transaction. and then this gives me a success, which is the corresponds to this right case in this computational result. And right now I'm just saying we have some output, a pair of output and Leo state that I just call X, and there exists such a pair that our computation yields the success X result. And then we can do the same thing with a slot step, which also gives us success. And both of these have proofs, and the proofs is, so here it's basically proof by computation. It just says compute what you have, and then that's the proof. And just to show you that we can actually sort of look at this result in this case. So here I'm just, so I'm taking an abstract transaction, right? I'm not giving a specific transaction value. Actually, this works for any transaction, and it's a bit like symbolic computation in this case. And so I'm passing this in, actually in this correctness proof, and now I'm projecting out this value X. So this is what's happening with this proj 1, and then it gives me this gives me the pair, right? So this is the empty output from Leo, so it doesn't really give me a reply. And then there's the new state, and here we can see in this new state is now our transaction TX. And then, of course, we can use this to generate longer traces if we want. So this compute trace is just doing multiple steps. So we need to solve some performance problems right now to actually make this sort of useful for conformance testing. But at least it sort of works in small cases right now. Okay, and I think that's all from our side.
Thank you, Andre. Okay, let's see if, here we go. Okay, next up is the DataQ system design. I'll share this update real quick because Roland wasn't able to make today's meeting. So as a reminder for new listeners, it's a tool that lets you use probabilistic language. It lets you create expressions that describe the behavior of a protocol. So specifically how information travels within the network from one node to another. And this also includes computational delays, introduced by producing processing information from the nodes. And our team has reached a point here where we can compare outputs of both simulations, which you can see in the graphs. This is the input block diffusion. And since December, we were able to improve the DataQ expressions by switching from like an average case to a best case modeling. This means the expressions we define represent the optimal diffusion, or in other words, the shortest path in the underlying topology. And moreover, which added to the better alignment, was that the simulation traces have improved over this time. And this led basically to us being able to parse out relevant events better for modeling the input block diffusion. And yeah, that matches quite well now with what the DataQ model is simulating. You can see the red lines here are from the simulations, so Rust and Haskell respectively. And an important thing to note here is that this was done using the same underlying network topology. There are slight discrepancies, as you can see. So these results would likely get better as we improve the expressions that we use. But we've identified some causes for those differences, and those go back to what Duncan was touching up on earlier. That the Haskell simulation, for instance, is modeling the bandwidth effects to be more realistic, and those effects are currently not part of the expressions. So what's next is to dial back some of those features. especially for the Haskell simulation, get the expressions to match the behavior, and then add them back step by step, essentially. And that way we can explain discrepancies better, possibly adjust the expressions that we're using, and increase our DataQ fidelity. And with that, we come to our last update. Simon, I think you're next for the Rust simulation.
Hello. Quick mic check. Can you hear me?
Yes.
Right. Great. So this month with the Rust simulation, well, first, just a quick reminder, we've got 2 simulations of Leios right now, the one written in Haskell and one written in Rust, that are kind of serving different purposes. The purpose of the Rust one is more to model the entire network at a larger scale, but more coarse-grained simulation than the Haskell simulation. So our objectives are related to performance and to helping improve people's understanding and intuition around the Leios protocol. So with that little bit of context in mind, our progress updates for the last month, our simulation of Leios is more detailed now. The general trend over the last month has been to update the Haskell simulation is kind of simplifying its model of, for instance, the network, and the Rust simulation is adding more detail to try to bring those simulations into alignment so that it's easier to compare those results. So the Rust simulation is also now simulating CPU usage across nodes, either bounded or unbounded. We're working explicitly towards alignment with the Haskell simulation. We've started, the Rust simulation is now accepting the same inputs as Haskell. The output isn't the same format, but it's compatible enough to power a lot of the other work that's been shown in this demo. And as always, we're working on bug fixes and performance improvements, because one of our ultimate goals with this Rust simulation is to be able to simulate the entire mainnet, a few thousand stake pools, a few tens of thousands of relay nodes. We want to simulate the entire mainnet running Leios with a higher transaction volume than mainnet is currently using today, like 10 times, 100 times, 1,000 times the volume of transactions that are going into it now. And so the performance of the simulation is kind of important, because we need to be able to simulate a lot of data for a long time, and it's tough to use that if it takes days to run a simulation of like 5 minutes. I also have a new piece to demo. We are working on a visualization of the output from the Rust simulation, and we have a couple of goals with that visualization. One of them is to serve as sort of a learning tool for Leios, helping people understand more intuitively how the Leios protocol works and what kind of behavior latency they should expect from using it. So we've, sorry, I'm trying to share my screen now. So we've updated our Leios simulation to include a visualization of the blocks getting generated as the simulation runs. So now in this blocks view, every time a block is generated for the, every time a normal Cardano block is generated, we update this graph showing how many transactions are in the block. If you click on one of the slots, you can see, well, a slot that's not using any Leios transactions. It's not very interesting. You click on the block and it's just a block, and it contains some number of transactions and they take up some size. But if you click on a transaction, or if you click on a block that does have transactions bundled from Leios, we're working on a way to visualize what exactly is in that block. So you can see here on my screen, there's the block itself, which it was created in slot 94. It's got some number of transactions, and it's referencing an endorsement block, which was created in slot 60, 34 slots earlier. And that endorsement block is referencing a bunch of individual input blocks, which contain some number of transactions. And each of those has some size. And you can see in the broader blocks view, you can see that the transactions from the Leios protocol ultimately, you can see the higher throughput that comes from the Leios protocol. It's there's a lot that this is not visualizing yet. There's a lot of detail that we would like to add to this in ways that make it easier to understand what exactly is going on. Like, we want to eventually show more about the voting process. We want to have a visualization of the resource usage for individual nodes in this graph. But this is kind of our next step towards something like a friendly visualization. Any questions on that?
Getting a lot of cheers. Great update. Very impressive. Thank you.
Love to hear it.
We also have, we're almost through. That's like the last slide of the presentation. We wanted to come back to some of the questions that were raised last time. I think most of them were from you, Charles. So one of the core questions was whether there are downstream effects, or what are the downstream effects of deploying Leios? And we have started an internal discussion. It's still ongoing, and at this point of time, we don't feel comfortable sharing some of the results because I think they will likely change as we make progress with our design iterations, especially in relation to the mempool. So we will definitely come back to that question in future monthly updates. And then the second part was the adaptability of nodes, I believe. There were a few questions around this, such as, could the mempool be sized to the throughput of the system? So that's currently already the case. So, and this will likely stay with Leios as well, where we have a default mempool size that's a small multiple of the current block size. If we find issues with that, then we can obviously adjust. And another question was, can the system be sharded according to the resources? So there was a comparison made between, I believe, supernodes and Raspberry Pi. And in short, the Leios design does currently not involve sharding in this regard. So there are ideas in research that require some more work. And as of now, each node basically has to validate all blocks. So hence, in a traditional sense, adding more nodes does not increase the throughput. And each node must basically cope with the throughput of the whole system. And then the last question, can the system self-regulate instead of manually fine-tuning? And this also goes back to the previous question, given that the load is imposed on each node through the choice of the protocol parameters, it remains like a democratic vote to drive like adaptation. So it's not, maybe in a sharded design, this may be different, but in the current system, there is no local or automatic choice that a node can make individually to adjust. So I hope that answers those questions. And with that, we're basically through. Thank you very much for listening. And yeah, feel free to ask questions. We have some time left. Thank you very much.
Thanks, everyone. Thank you. Bye-bye.
I monitor the YouTube chat, but there's no question in there either, so we should be fine. Okay.
Got a lot of viewership this time.
Okay, I can stop the stream now. Well, thank you, everyone. It was the first live. It went well. Thanks a lot. Thanks a lot. It was